observation. Now, as I told you, I am going to explain to you what is a transition matrix. That we study already. Transition matrix is a matrix chuyển cơ sở. Now suppose that T from V into V is a linear translation. That is a T from V into itself, nothing changed. Now, with that we have V will be mapping to T of V. Suppose that we have D is a basis for here, and with that we means that, as I told you before the break, now we have a matrix of T relative to the basis B, because we choose B on both sides, on the domain and codomain, and T is a linear translation from V into itself. Then we have a matrix of T relative to B. It is defined by, if we consider T of V1, T of V2, T of Vn, that's the coordinate column of that according to the basis B, and then we get A like that. And with that, with the matrix A like that, we know already that T now is given in the form of a matrix like as follows. Coordinate column of T V will be equals A multiplied by coordinate column of V. That is the definition of A. Now suppose that on V we are given another basis B prime, and now suppose that B prime consists of W1, W2, W2 up to Wn. You should remember that the number n here and here are the same, because the two different bases of the same vector space needs to have the same number of vectors. So here, if here is n and here is again n, that is always like that. And then again we have the matrix of T relative to B prime will be denoted by A prime, and we found it, we define it by the same way like for A. But now we consider T of W1, T of W2, T of Wn, and we consider the coordinate in the basis B prime. And with that, again, now T will be given by this form. T of V is the coordinate in B prime equals A prime multiplied by the coordinate of V, that is relative to the basis B prime. So for basis B, we have that formula. We have for the basis B prime, we have that B prime. We want to know A and A prime, how they related to each other, because A and A prime, they are matrices of the same mapping, of the same linear translation T. We just only to consider it in different bases. So how they related to each other? Here it is. Suppose that B is a transition matrix from B prime to B. It is defined like that. I will not repeat it here. You have to read it in the slide before. We write down P, that is a transition matrix from B prime to B. With that, we know the coordinate of V relative to the basis B equal P multiplied by the coordinate of V relative to the basis B prime. That is reason why P is considered the transition matrix from B prime into B. It means it changes the coordinate from B prime into the coordinate into the according to the basis B. And also we have a transition matrix from B into B prime. It is here. It is a P inverse. That is a transition matrix from B to B prime. And we can define it by this one. And with that, we have a similar formula, but now we change the role of B and B prime. Now, the coordinate of V relative to the basis B prime equals P inverse multiplied by coordinate columns of V into relative to the basis B. So that is all the ingredient we have now in hand. So now, what is the relation between A and A prime, B and B inverse N? Then you can take a look at the picture here. We can go from from V into here. From V into here by the mapping T, the linear transformation T. But here we consider the basis B prime. So the basis, because we consider the basis B prime, so we have the standard matrix is A prime. Yeah. So at the bottom we have A prime. But now we at the top here the same linear transformation T, but now we consider on both sides V domain and codomain here, we consider the basis B. We have standard basis B, standard matrix A. So down here we have the standard matrix A prime, and here we have A. But from here to there, here we do nothing. We just only to change from the coordinate B prime into B. And from B prime to B, that is a matrix P, because here. And then from here to there, it means we change from the basis B into basis B prime, and it is given by the matrix P inverse. And then you see, from here to there equals, we go from here to there. And we go here by A prime, and we go here by P A and P inverse. Or I write it once again in the next slide. Here, we have two ways to get from V, the coordinate of V into B prime, into the coordinate of TV into the basis B prime. That is, we have two ways going from here to there. The first one, I call it the direct way, means now we get it by multiplying with the matrix A prime. We get it here. Or by the red arrow here. We call it the direct way. But also we have the indirect way. The indirect way, like that. We go by that way. And you see, that way is exactly the composition of C map from here to here, from here to here. Okay. And because of that, if we remember what we studied before the break, that we have a matrix P inverse multiplied by the matrix A and multiplied by the matrix P. So it is here. And because we go this way and we go that way, the reason are the same. So we can conclude that we have A prime equals P inverse multiplied by A multiplied by P. So that is what you need to remember. You need only to remember that one. And you need to remember what is the P, what is the P inverse, what is the A, and what is the A prime. Okay. That formula gives us the relation between two different matrices of the same linear transformation in different bases. And here is some examples. Now, suppose that T from R2 into R2 is a linear transformation given by the formula like that. And if on R2 and on both sides we consider the basis b prime like that one. And the example require you to find the matrix A prime for T relative to the basis B prime. How you can do that? First one, A prime, the A prime will be that one. T of that is the first solution. We do the direct calculation. We calculate T of the first, T of second, and we write it in the basis coordinate in the basis B prime. So what you get? T of the first one to be that, and we express that according to the basis B prime. We get 3 times of the first minus 1 time of the second. Then the coordinate column will be 3 minus 1. If we take the second one, T of the second vector, you get that one. And again, if we express that in the basis B prime, you get the coordinate columns minus 2 and 2. And because of that, A prime to be that one. So that is the first method to find A prime. But the second method will be use what we expressed in the previous slide here. First, standard matrix for T is already now. T of that equals that one. And then transition matrix from B prime to B to be that. That is the way we define the transition matrix from B prime to B. It is that one. Then finally, we can. It is very easy to find that the P inverse to be that one, or it is a transition matrix from B into B prime to be that one. Then the matrix of T relative to B prime will be, now we just only to apply that formula. A prime equal P inverse multiplied by A multiplied by P. We get that one. Obviously, if we consider the method in this line and in the previous line, the direct calculation is much easier, much simpler. But in case the size of linear transformation T is bigger, that method is much simpler than the other one. And here are some more exercise, some more example. Suppose that you are given two bases B and B prime of R2. B to be that one and B prime to be that one. Suppose that they both are bases for R2. And suppose that we know already the matrix for T relative to the basis B is that one. Then you are required to find the matrix of T, but now relative to the B prime. In that case, you don't know what is a T, but it is very easy for you to know. It is you can do it because the transition matrix from B prime to B, it is very easy to write down. That is a P to be that one. You calculate it and express it in the basis B. You get that matrix. That is a transition matrix from B prime to B. And also the transition matrix from B to B prime. We denote it by B inverse. You can get it by this one. Then A prime will be that one. You can multiply same matrix to each other. You get that one. So that is now in this example is very easy for you to find. And the next one, you are required to find a matrix for a linear transformation. The linear transformation T that is from R2 into R2. It is given in the example number 2. We did it already, and you are required to find the coordinate of V relative to B prime. T V of B and TV of B prime for the vector V. And here the vector V has a coordinate -3 and -1. So how you can get it? Here, the coordinate of V relative to the basis B equals that. And we know already in the previous slide, we know already P, the matrix, the transition matrix P is that. Then you can find very easy that the coordinate columns of V relative to the basis B to be that one. And similarly, T of V, that is coordinate in the basis B will be A multiplied by coordinate of V in B. And it is here. And so on. You can apply anything we get in the previous slide into this example. You can get anything here. Now we are going to define what we call similar matrix, or in Vietnamese we say ma trận đồng dạng. Now suppose that we are given two square matrices A and A prime of the same order n. Then we say A prime is similar to A if we can find an invariant matrix P of the same size n, so that A prime equals P inverse multiplied by A multiplied by P. That is the division of two matrices which is similar to each other, A and A prime. Then if you look back at what we studied from the beginning of today, we see that two matrices of the same linear translation in two different bases are always similar to each other. That is the meaning for the similar matrices. And here are some property for similar matrices. That is, suppose that we have A, B, C, a square matrix of the same order n. Then A is always similar to itself. I mean, A is similar to A. In that case, I choose P to be the identity. And A, if A is similar to B, then B is similar to A. So everything is very easy for you to verify. And also, if A is similar to B and B similar to C, then A also is similar to C. And here, the explanation is already written in the slide. And the example we have is here. A and A prime are given as on the screen. And you will see that A and A prime will be similar to each other. Why is that? If you consider P to be that matrix, P to be that one, then A prime equals P inverse multiplied by A multiplied by P. That is very small size matrices, so it is very easy for you to do calculation here. The next one, A to be that and A prime to be that one, they are also similar, because if we take P to be that, you can also verify the formula here. Now we can, going back to that, we compare two matrices of the same linear transformation. Now suppose that T from R3 into R3. And suppose that we have it has a matrix A. The matrix A. That is a matrix according to the standard basis. Now you are required to find the matrix for T, but now relative to the new basis B prime on the screen. How you can do it? It is here. We can apply what we studied before. first we need to find transition matrix from B prime to the standard matrix B. I call the standard matrix to be B. Then the next one, you find the transition matrix from B prime into B, from B into B prime. It is a P inverse, and P inverse also, if you want, you can find the P inverse from here. It is not so difficult to find. It is. Then the matrix of T relative to the new basis B prime will be the following. Will be that one. Now you need only to do multiplication of 3 matrices like that, and you get that one. And I'd like to tell you, to insist to you, that now the reason is already in the diagonal form here. That will be the subject of the lecture number 7. But however, before that, please remember that we find A prime, that is a matrix of T relative to a new basis B prime. And we observe that in the new basis B prime, the matrix of T is of diagonal form, like that. And now I give you some advantage of diagonal matrix. Why is that? Because in the previous examples, I show you that if we choose a suitable basis, the matrix of a linear transformation can be the diagonal form. So why we need the diagonal form? Because it has some advantage in calculation as follows. Suppose that D is a diagonal matrix like that, then D to the power K will be that one. You can try it by yourself. First, you take D multiplied by D, I mean D square. You will get D square, D1 square, D2 square, Dn square. And you multiply them to D once again, you will get D1 to the power 3, D2 to the power 3, and up to Dn to the power 3. And all other entries are always 0. Very easy to verify it. And also, with the diagonal matrix, you have transpose of D equal D. And the inverse in case that all the entry lying on the diagonal are on non-zero, then the first one, D is an invertible matrix because the determinant will be the product of D1, D2 up to Dn, and that product is non-zero, and determinant is non-zero means D is an invertible matrix. And in that case, in the diagonal case, the D inverse will be given by that. It is again a diagonal matrix, but the entry will be 1 over D1, 1 over D2 up to 1 over Dn. So that is the advantage of a diagonal matrix. So that is finish of the lecture number 6. And we begin right now the lecture number 7. Let me find the lecture number 7. It is here. So you see, the lecture number 7, but if you look at the title, the eigenvalue and eigenvector, that is what we studied several weeks ago. But however, the main object of the lecture number 7, that is diagonalization and orthogonal diagonalization, chéo hóa và chéo hóa trực giao. That is what we need to study in the lecture number 7. And in front of us, there are left only 2 more lectures. not including today. We have 2 more lectures. So we begin right now, because I want to repeat something for you. The eigenvalue and eigenvector, that is what we know, we study already. So here just only a repeat of what we study. First eigenvalue. Suppose that we are given a matrix A of size n by n. Now we consider only square matrix. We need to find a non-zero vector x inside Rn, so that A multiplied by x as a column matrix will get a multiple time of x. Or if we write it in the formula like that, suppose that A is an n by n matrix, lambda is a number of scalar, x is a non-zero vector in Rn. If we have equality Ax equal lambda x like that, lambda x here means a multiple time of x. If we find a non-zero vector x satisfies that one, x the number lambda will be called the eigenvalue of the matrix A, and the non-zero vector x will be called eigenvector corresponding to the eigenvalue lambda. And if you look at the geometry, you have that one. X is here, and lambda x must be up to that point. And AX equal lambda x means that you can see. Now, the examples we know we study already in the lecture class several weeks ago, that is here. We consider A to be that, and x1 and x2 to be 2 vector or 2 columns matrix like that. Then you see AX1 equal that, and because of that, the first vector x1 will be an eigenvector, and that eigenvector corresponding to that eigenvalue 2. The next one, if we multiply A by the vector x2 or the column matrix x2, you get that one. And again, now x2 of 0, 1 is an eigenvector corresponding to that eigenvalue. So that is an example about the eigenvalue and eigenvector. Now that one we have not yet studied, as I remember. That is now, suppose that A is a square matrix of order n. Suppose that we fix an eigenvalue lambda of A. Now we consider the set of all eigenvector of lambda. Now the set of all eigenvector corresponding to lambda, we consider that together with zero vector, they all will make a subspace of Rn, and we call that subspace is an eigenspace of lambda. So why we need to consider together with zero vector? Because the eigenvectors we require, it is always non-zero vector. But you remember that in any vector space and subvector space, it always needs to have a zero vector. So that is the reason why here we need to add the zero vector. So because of that, in your exercise, if you are required to find eigen space of some eigenvalue, you need to remember to add the zero vector to the eigenvector, not only to find all the eigenvector. Here is some explanation why it is a subspace. Once again, I repeat to you, in order to verify something, some subset to be a subspace, you need to verify property number 1 and property number 6 in definition of a vector space. That is very important things. And here is some examples. The eigenvalue of A will be that. Here you see, it's very easy. A, we are given A to be that one, and suppose that V equal x, y, that is some vector inside R2. We need to find eigenvalue and corresponding eigenspace. Now, for vector on the x-axis, we have that one. X-axis means it has coordinate x0. We multiply them with the matrix A, we get that one, minus 1 of x0. So with that, we get eigenvalue lambda 1 equal minus 1, because here. And that is one of eigenvector. Suppose that x is non-zero, because the eigenvector need to be non-zero vector. So if you consider the eigenvector, x must be non-zero. Then if you consider a vector on the y-axis, we get that one. Again with that. And because of that, that one will be an eigenvalue lambda 2 equal 1. And you can see, if you look at it geometrically, if you multiply a vector x, y in R2 by a matrix A, you take any vector x, y, and you multiply by the matrix A from the left, you will get, what you get? You will get a reflection by the y-axis, or by geometry, you will have that one. Yeah. X, y now will be minus x, y here. So because of that, you will see the eigenspace corresponding to lambda 1 will be the x-axis on thing here. On vector lying here will be the eigenvector. And the origin is not an eigenvector because it is a zero vector. But however, we need to add zero vector inside that to get a subspace. So the first eigenspace corresponding to lambda 1 to be that one. And because of that, the second eigenspace corresponding to lambda 2 equal 1, that is y-axis. Yeah. On vector lying on the vertical axis, they are eigenvector corresponding to 1, except the origin, because the origin is the zero vector. Zero vector cannot be an eigenvector. So in that case, we have a two eigen space. The first one is here, and the second one is there. So that is an example for you to see what is the eigenspace. Now I repeat just how you can find an eigenvalue and eigenvector. Suppose that A is a square matrix of order n. Then eigenvalue of A will be a number lambda satisfying the equation determinant of lambda I minus A equals 0. And the eigenvector of A corresponding to eigenvalue lambda will be the non-zero solution of this homogeneous system of linear equation, like that one. And that we know already from previous class. I just only to repeat it here, because next week we continue from that point. So once again, I repeat some name for you. Because Ax equal lambda x, so it implies that lambda I minus Ax equals 0. And that is a homogeneous system of linear equation. But however, because x is eigenvector, means x must be non-zero. It means that we need to find non-zero solution for a more homogeneous system of linear equation. And we know already that homogeneous system of linear equation will has non-zero solution if and only if it has non-zero determinant. It has zero determinant. That is reason why we need to find lambda satisfying that equation. and that equation determinant of lambda I minus a equal 0 Queen has the name characteristic equation of A, that is here. And the left hand side determinant of lambda I minus a will be a polynomial in the variable lambda of the order n. It will have the name characteristic polynomial of A. So that is what here is some example. So I will leave it for you to read, and I want to stop today here about that. Now, before finish the class today, I want to show you one more thing. That is what you are waiting to see here. That is something about the midterm exams.